and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion science and engineering. I'm Ekaterina, and I would like to introduce our speaker today, Dr. Andrey Litnovsky, who will be speaking about advanced materials and new concepts for future fusion devices. Professor Litnovsky is a graduate of Moscow State Engineering and Physics Institute (MEPhi) in Russian Federation. His PhD in physics and mathematics in 2001 was awarded for the work made in MEPhi and in Kurchatov Institute in Moscow. And Andrey Litnovsky works for Forschungszentrum since 2002, studying edge plasmas of fusion devices, plasma surface interactions processes, and performing material research and developing diagnostics components for International Tokamak Experimental Reactor. As a senior scientist in Jülich, Andrey Litnovsky is leading a number of European and international activities on plasma wall interactions and plasma diagnostics. Being a chief of operation of Texture Tokamak until the end of 2013, he did a great job among research projects, and he coordinates the development of advanced alloys for a future fusion power plant, leading the Smart Alloy Research Group in Jülich. In 2020, Dr. Litnovsky became a teaching professor at the National Research Nuclear University MEPhi, his alma mater. Professor Litnovsky actively contributes and promotes international collaboration and educational programs. So I'm looking forward to hear about advanced materials and new concepts for future fusion devices. And without further delay, I give the word to Professor Litnovsky.
Thank you very much, Ekaterina, for this nice introduction. Thank you very much, dear colleagues. I will minimize the poll, not to do something very weird. Yes, this lecture, dear students, dear colleagues, maybe future colleagues, will be devoted to advanced materials and new concepts for the future fusion devices. As you might see, many of you have seen today, there was a press conference on JET results. These are milestone results. They're really very important and really groundbreaking results on DT operation, just streamed right now. And we will be speaking, in fact, not even about JET, not even about ITER, the next generation fusion device, but about the fusion power plant. And this talk, of course, is made with the contributions of our dear colleagues from all around the world, of course, from Jülich, from our MEPhi University in Moscow, but also from China, Hefei Institute of Technology, our Dutch colleagues, Polish colleagues, UK colleagues, and this participation is greatly acknowledged. So speaking about the fusion power plant, this will be the fusion device with unprecedented power parameters. So for the fusion power will reach 2 gigawatt. For lifetime, it will be still pulsed and arranged for 20,000 pulses, but with pulse duration of 2 hours. It is really quasi-stationary with the fusion gain of 40, and will feature the power load on the first wall of up to 2 megawatt per square meter, while the power load in the divertor can reach 20 megawatt per square meter. And under these conditions, the materials facing the plasma, you can see these materials at the walls of the vacuum vessel and in the lower part in the diverter. So it was decided to select as a baseline material tungsten, which has a number of very good features, a number of advantages like high melting point, relatively low activation, low sputtering by plasma particles, relatively benign tritium retention. And this material was selected as a baseline material. To understand, however, what does it mean, this megawatt per square centimeter, this power density, we can go to the next slide, and which shows, in fact, in live examples, what does it mean. So you can see that 20 megawatt per square meter actually is corresponding to the surface of the space vehicle during the re-entry processes. And the effects, the transient effects like disruptions, can feature up to 2 gigawatt per square meter, which is the, let's say, characteristic feature of the fusion devices. So this is really quite important and quite challenging numbers, what the materials will be facing in. And if we look to the conditions which are awaiting our materials in the fusion plasma, we can see this area of irreversible material degradation. This is where we really lose the material, of course, and this is the power density, and this is the duration of the path. So we can tolerate disruptions and vertical displacement events for a very short time only. But even if we look to the long pulse duration, and we remember that we will have the pulse of 2 hours in the power plant, we can see already that the tolerable loads, the power densities, becoming really quite small, which the material can make. So the time plays against the material lifetime. So that means that in the fusion power plant, in the reactor, already regular operation becomes challenging. From the current tokamak, and I actually work quite in almost all largest tokamak, we see the performance challenge which is facing our materials. This can be dust from materials, it can be plasma disruptions, it can be the melting of components, it can be the cracking of the materials, which was observed on several devices. They are shown here and a couple of more. But the key difference from the current reactors and even from ITER with 10 minutes pulse for the power station or power station-like reactor, that during this discharge, almost all of these processes will be changing the material simultaneously. So they will happen simultaneously. And presently, there is no materials which can withstand these things simultaneously. Another characteristic feature of the fusion power plant, which resembles this from current fusion devices, is the neutron environment. So as we remember from the nuclear fusion reactor, from heavy isotopes of hydrogen, deuterium and tritium, they will merge with the creation of the helium ash, the fusion ash, the helium particle and high energy neutron. So we can see that the materials under this massive neutron impact will transmute, and after the 5 years of operation, we can see that already 6% of tungsten will transmute to these isotopes. Speaking about the neutron flux, and here we see that the neutron flux density as a function of energy per lethargy interval. So we can see that for MeV, 14 MeV neutrons, the fluxes can be as high 10 to the 14th Newton per square centimeter, which is really a great number. This is really challenging environment, which will change the properties. I would say, honestly, change, because they may influence this way or the other of the material. And this way was speaking only about the so-called regular operation. There is a safety challenge, and of course, in case of the power plant, the safety will play very much important role, and it will be actually by far excessive to the safety, as for instance for ITER. The temporal license of ITER actually took something like 50 meetings to handle off, and it is around 1,400 documents. So you can imagine for the first licensing of the power station, what we can face. Of course, the safety will also be can be divided for the safety during the regular operation, which is mostly connected with the tritium inventory, because the tritium is radioactive. It can be accumulated in the vacuum vessel. It can be actually pronounced by the neutron effects, and the concentration can be quite high, as we see from these results from meeting. But also important knowledge is actually the major accident, like an earthquake. Under these circumstances, the fusion power plant will face tremendous challenge and additional circumstances which will further complicate the operation. First, it is no immediate access of water and coolant, no electricity, difficult logistics, and the lack of manpower, which may make difficult to suppress the release of radioactive materials and dust from the vacuum vessel. So this should be, in fact, avoided. So in this case, the new plasma-facing material, and this is kind of the topic of this lecture, to show this concept, it will be the combination of the performance, safety, and technology, which are united in each of this material. In the course of this lecture, I will go from topic to topic to show the solutions for this challenge, starting from the performance. Looking to the performance, one of the perfect examples is so-called tungsten-fiber-reinforced tungsten. It is in a similarity like carbon fibers. We are introducing the small fiber like wires in the tungsten matrix. And the idea here is to make the energy dissipate. The energy which would rather go to the crack formation and destruction of the material will be dissipated by pulling out of the fiber, plastic deformation, bridging the crack, or deflection of the crack. So here there are the dimensions of the fibers, which are quite small. How this all works, show this movie. You see the crack goes, and then it enters the first fiber. It really branches, so the material actually continues to struggle against this. This is a second crack, which still takes time to break this fiber. To see with the numbers, if you apply the force and see the displacement, the tungsten, the pure tungsten, can be shown here. So you see with applied force, it simply breaks, so there is no displacement, it basically gives up. Whereas even for first non-optimized design, so you see after the first initial crack, so you can still tease the material, so it can still expand and go further. So it still fights against this. And also you can see already the difference in the maximum force which is applied in order to get this crack at all in this material. Whereas with optimized tungsten-fiber-reinforced materials, you can see that the maximum force applied is already double as much. And you can see here before the first big crack formation, the material is actually still expanding and going step by step and not going really to the zero power. Which really shows the perfect pseudo-ductile behavior, and we see that this material really overcomes the intrinsic brittleness of tungsten low temperature. There will be another example how you may do this, but let's look to another concept for the divertor, for this 10 to 20 megawatt. It is similar in the sense that we are using mostly the same fibers, not in the matrix, but put as a material. It is so-called microstructured tungsten. So there are a series of devices with the same, in fact, dimensions of 0.15 millimeter diameter, casted molded on the copper via infiltration or diffusing bonding on the steam. The essential advantages of such a system is the diameter of vias is smaller than the crack distance after the thermal cycling or thermal shock. So it basically will isolate within this small diameter within the small fiber, should isolate damage. It may provide high neutral pressure because plasma attaches on the larger surface, and may then provide a longer long-term retention. But let's see how it all works. To study this, there were several laser pulses with the power density of 0.64 gigawatt per square meter, simulating transient effects. So in total, it was 200,000 pulses of 1 millisecond put to the ITER grade tungsten, or the tungsten made with ITER specifications, and on the microstructured tungsten. To be honest, the ITER grade tungsten showed the damage after the several hundreds of these pulses already, whereas the microstructured tungsten survived all these 200,000 pulses. This is an incredible number. without detectable damage. To be honest, also the deuterium retention was larger, which is not good for such a structure, but the operating temperature of such materials will be high enough to outgas this deuterium. So this actually showed the incredible performance under the repetitive high power loss. Speaking about the pseudo-ductility, what about different technology? And this was actually brought by our colleagues at Karlsruhe, which noticed one first glance very simple example. If you have the tungsten foil, which is thin enough, and you know the tungsten as such is tremendously brittle material, so you can really put this on the floor and it will crack or it will break and on the part. But if you take this form, which is cold worked and rolled, and you see the grains are highly unhomogeneous, so you can actually bend this roll, nothing will happen. So it is ductile at room temperature even. So the idea was, why don't we use such a design in order to get the components of the bulk material? So this came to the idea of so-called tungsten laminates, which is, as an example, shown here as a layered tungsten and in this case the silver copper epectic system. How this all works shows this small video. On the left side, which I will start right now, it is the pure tungsten at room temperature. It breaks simply because it's absolutely brittle. If you put the tungsten laminate, which is on the right, you can see how it really bends. And it bends, in fact, actually, it's not getting even destructed. So it was actually quite viral video from the Karlsruhe colleagues which shared this material with us. So these laminates obviously work. And this gave actually the high pulse to the number of the fusion-related applications. As you see here, this is the interior of the pipe here. And this is the zoom in what is going on there. So you see here corrosion protection layer, the copper interlayer. Actually, it's a copper tube, in fact. And this is a tungsten copper laminate where you see the changing layers in between, whereas the finally ending up in the tungsten armor. So, and there is a lot of various designs of such a laminated materials presently available for the fusion devices. So these are primarily used for the water-cooled components, and tungsten copper laminate in this particular case is increased the strength of the copper chrome zirconium pipe and made very nice thermal management. So this concept is already quite widely investigated. Going to the safety of this, there is another suite which comes and the help to the conventional materials in the advanced concepts. Starting again from the regular operation, as we just, let's say, heard, we will have tritium permeation problem. The tritium from plasma can enter the components of the material, and this will be half of the problem if it remains in the components. But if it goes, for instance, into the cooling water, it will create a tritiated water. This will be radioactive water, which is virtually incapable to catch. So we need to contain tritium within the plasma-facing components. How it can be done? With the means of so-called tritium permeation barriers. So the efficiency of these barriers should be intransparent for the tritium atoms. So on the high pressure, high concentration side, like plasma side, there will be a lot of tritium. After the barrier should be very few. It is realized with a quite tiny 0.5 millimeter thick ITER layer deposited on the steel, because steel is structural material which is located after the tungsten. And you can see here the attenuation. How is our efficiency? How much we suppress this deuterium flux? And you can see as a function of the pressure, actually up to the very high pressure of 1 bar, which is unrealistic for fusion, but for the test purposes it is good, at 500 degrees C. And you can see that the pure structural material Eurofer, this is a theoretical multi-synthetic steel, already is quite a good barrier, capturing actually almost everything from 100,000 deuterium atoms. Only one comes through. But the permeation barriers, even the non-optimized, increasing this at least 10 to the 100-fold, whereas the optimized ITER can make again more than 1,000-fold increase in the efficiency of tritium capturing in the plasma components. And this is during the regular plasma operation. If we speak about catastrophic accident, there is another scenic concept comes to the play, also called SMART concept, which is smart states for self-passivating metal alloys with reduced thermal oxidation. Why do we speak about thermal oxidation? Because we are speaking about the really terminal accident, supposing the earthquake destroys completely our fusion power station. And there is a modeling which is referred here for various designs of the power station. There will be quite a challenging scenario there. As we see, there will be huge neutron environment, and these new neutrons will activate the material, which will produce the nuclear decay heat. So it will heat, in the absence of destroyed coolant, the vessel components just by this decay heat. And the temperature at which will heat will exceed for tungsten cladding 1000 degrees C. Then imagine the earthquake, it destroys the vacuum vessel, and air enters the vacuum vessel. And you can see that with all these conditions, with this radiative cooling, this high temperature can last for several months. In the contact with the air, tungsten, you can hardly imagine that such a heavy material actually creates, oxidizes and creates the volatile oxide. So tungsten oxide is volatile, it is aerosol. And if we calculate, according to our data, the amount of this creation of volatile aerosol, we can end up, supposing the same surface area as presently in ITER, in demo, in this fusion power plant, we can deal with 10 to 150 kilograms of radioactive tungsten per hour escaping the vessel during an accident. And of course, nobody wants to have this. Yeah? Now, having all these conditions with destroyed logistic and so on and so forth, if we would have a chance to make a kind of inbuilt safety in our material that will react to the accident without any action from the human being, it would be a nice opportunity. And this is actually the basis of the smart alloy concepts. So these materials are designed to be chameleons, which really change their properties depending on the environment conditions. So they detect these properties, the material itself. So during the regular plasma operation, the tungsten alloy, which will be alloyed with special alloying elements, chromium, and in our case, yttrium, those elements are lighter. They will be sputtered by the plasma almost immediately, leaving the full pure tungsten surface facing the plasma. And this is what plasma actually needs. It needs low sputtering, low tritium retention, and all other advantages, high melting point of tungsten. So the tungsten protects the underlying elements from the plasma. So it will be the protecting layer. During the accident conditions, the remaining in the bulk alloying elements will diffuse into the surface of the tungsten, create their own oxides because they're more chemically active for the oxides, and this oxide will prevent tungsten. Now the roles are changed. The alloying elements are preventing tungsten from oxidation. So, as I said, these materials, one of the most advanced, containing tungsten, chromium, and yttrium, and they are in fact quite scenic. To see how they look like, we will have the results of the very short, so to say, oxidation for 20 hours in humid air at 1000 degrees C. And these are the results of the so-called atom probe tomography. This is very high-end surface technology, which basically sucks the sample and reproduces, analyzing all the elements. Each of these point is one atom. So it's all quantitative. It's not really only the movie. So one can see the bulk of the smalt material, the chromium. Tungsten is not shown because otherwise you will not see anything. So this is the chromium inside, and this is the yttrium, which is located in the grain boundary. You can see right now the grain boundary. So this is a yttrium nanoparticle, 10 to 30 millimeters. And this is all quantitative. We had our colleagues in Oxford and in Warsaw, which simulated for us these effects. What we found, let's say, experimentally and with modeling, that the oxygen, here blue, is only within the yttrium particle. So yttrium plays a very important role, being very tiny amount. It sucks like a vacuum cleaner. All the oxygen clean the boundary and makes the so-called perovskite-like mixed oxides, which are shown here. And it was tremendous agreement between the modeling and experiment. So the yttrium was found experimentally in this particular stoichiometry exactly as predicted by the modeling, at grain boundaries as predicted by the modeling, and in very tiny particles. What else the yttrium does? Yttrium, as we see, bounds oxygen. So the chromium can move further without any obstacles to form this protecting layer to protect tungsten from oxidation and sublimation. So basically, and thus stimulate the chromium transport. So the effect of the yttrium is fantastic in these conditions. And this is, as you see, highly nano material. To see how this material works, it is actually shown here in numbers. So it is a mass change in the course of oxidation, in the course of the contact in the humid atmosphere at 1000 degrees C. One can see the pure tungsten. In fact, as this graph goes up to 55, so it's really rockets. The mass gain because of oxidation, so material becomes thicker, of the smart alloy is very, very much benign. But it is not oxidation which makes the problem. So material just becomes thicker, loses the shape, and so on. It is the subsequent sublimation which leads to the radioactive release. And this is actually shown here. It is much less process, it's much less intensive process. You can see the sublimation of tungsten layers within this limit. Look to the sublimation as a negative mass of smart alloy. It is essentially zero. Well, without cheating, we cannot detect here the sublimation of chromium, but it will not exceed this line. So you see the factor of 40 suppression of tungsten sublimation by these fantastic nanomaterials. Of course, since it is, you see in the numbers, it is also nice to see how it looks in the reality. These are the results of only 10 hours of the exposure of these smart alloys in the air-containing atmosphere at 1000 degrees C, at atmospheric pressure. So you see nice and shiny tungsten sample, and this is what happens after the 10 hours. So it completely loses the shape, it continues to oxidize and even open the hook, as you see here. Yeah? What will happen with the smart alloy initially so shiny? It will just become black. And if you completely preserve the shape, if you scratch this a little bit, it will be shiny because there are only a couple of micrometers of this protecting layer. So nothing happens with it. So they indeed feature quite impressive resistance to the oxidation. Of course, since it is plasma-facing materials, there is very important point is to see how good or how bad they are in the plasma. And for this, we made dozens of experiments in several facilities to see the effect. The materials were either simultaneously exposed with tungsten, or it was consecutive identical exposures made where the smart alloys and pure tungsten samples were subject to deuterium steady-state plasma, like in the power station at the temperature like in the power station in first wall. And we had the chance to compare the results with a baseline material, pure tungsten. And this is what you can see. First, it is a surface recension. So how much material was sputtered? Tungsten versus smart alloy. You see the numbers are the same. So basically, after this protecting layer of tungsten was formed, the materials are sputtering nearly the same. I mean, not nearly the same way. If we look to the mass loss due to the sputtering as a function of the flux of fluence, which is calculated to demo operation, these are the fluence corresponding to 20 days of continuous operation of the power station. What we see, smart alloy is green, tungsten is gray. Smart alloy, in fact, loses less mass because of the lesser density, which is also a very good result. But important is also this red number. This number shows if we sputter this in our model system and nothing happens with the smart alloy, so it will be sputtered as we predicted, no additional parasitic transport of the alloying elements which can increase the sputter. The ratio of the mass of smart alloy to tungsten should be around 0.22, 0.82. And this is what we see. In fact, there is nothing, no additional measurable losses of alloying elements, which we need for our accident scenario, was measured in this experiment. And this is the good result. Finally, of course, the ultimate test, because we first have regular operation, then, for God's sake, but it might happen, the accident will happen. How the smart alloy, which were exposed to the plasma, do they have this still enough material to, let's say, suppress the oxidation? The ultimate test of them was the oxidation resistance after the plasma exposure, to have the full picture. And here the first, in this graph, which shows what is the amplitude of change of the mass during the oxidation. We first were alarmed because the initial ideal samples, which I shown this quadratic cubic bricks, they're showing that they are not even, I mean, they have very tiny change of the mass because of oxidation, whereas the plasma samples show quite large of this. And we started to investigate why is this so. And it appeared to be the matter is not the material itself, but its shape. You look at the shape of the plasma material sample. It has the hole, it has this loop. You see these black parts, which we cannot clean. So these exactly parts, and you can see plasma geometry without any plasma exposure, has the same trend of the mass change. And the plasma exposed samples, which are here reddish, they are performing even better. The smaller difference, the better. But important message, after 30 hours of operation, this geometry effect vanishes and the only material plays a role. The material is good. The shape which is governing this change of the mass, it is simply burning out of the dirt during the manufacturing of these particles, of these samples. But the material as such works well irrespectively from plasma prehistory. This was a very important result. And finally, going to the technology of such a stuff. Of course, it is not, you've seen this all wonderful in nanometer area and so on and so forth, but how we are going to cover the power plant with all of this fancy material? We make use of the very sophisticated technology, and a couple of the examples are shown here. One of these, it is so-called field-assisted sintering technology. You will see now a small movie, and I will describe, so to say, in few details what is going on. In conventional sintering, you are simply pressing and heating, and this will take hours. During the field-assisted sintering technology, there is one effect which comes on top. So you're pressing the powder inside, very nicely isolating, and starting pressing. This is like usual technology. And now comes the game changer in these things. In field-assisted sintering, you are really pushing the pulsed current through the particles. And this allows us to heat this powder very efficiently and to melt, at least, or to deform these boundaries of the powder particles. And finally, it results in spectacular features, like making the materials with very different properties within one sintering techniques, with very different characteristics. And as you see here in this results, but the most of this effect and the highest effect, it is low cost and tremendous speed of such a sintering. You can imagine our smart alloy is being sintered the entire process in 15 minutes, but the sintering itself takes only 7.5 minutes, and another 7 or 8 minutes are for cooling. And speaking from this nanomaterials, we can see that these nanomaterials are already available in very microscopic areas, as well as in Germany and our Chinese partners. And if you look to a segment of the first wall, which is in ITER 5 to 5 centimeter, we have here 10 to 10. This already exceeds any of these fusion requirements, and we made quite a lot of them in the last year. So this is not a problem, and this was made using the industrial machine. Another technique which is used for, let's say, for advanced materials, it is additive manufacturing. In this additive manufacturing, you will see the small movie here. We use the energy of the laser or electron beam, which is sintering the powder. So you basically see the powder bed in which this laser is focused. And you see how precisely it can actually melt the powder particles on this way, which allows the creation of the shapes which you would never be able to sinter with at one process. It is fully computerized and it works nicely, so it actually reads the CATIA design, slices this, and transfers these slices of the material to this additive manufacturing device. So here it is a view of the material, below it is the powder, and on the top it is a laser system. So basically it really melts, shoots on the powder, and really melts and consolidates these particles. And at the end of this process, it will be one layer which is selected. Then the powder is filled in, and the next layer is produced. And so further, the entire detail is made by this technology. As soon as this detail, this part is made, you simply need to get off the residual powder, which can be afterwards recovered, and then here you have the results. So this is actually the front end of manufacturing techniques, and this is really widely used now in creating on the first wall components, like you see here, the tungsten blocks. The tungsten density made by advanced manufacturing, this is now the project supported by Eurofusion, can be as high as 99%. But this is not the end. If we see our material, which plasma-facing material needs to be joined to the constructive material, or the structure material steel, and if we see a number of the parameters which are very different from tungsten and steel, like thermal elongation is 3 times less on tungsten, heat conductivity is 3 times more for the tungsten. It's like a magic number, 3 times, but every time in different directions. So the idea is, as you've seen, you're adding the powder, but you can also change the powder. You can also mix the powder and make so-called functionally graded materials, gradually going from tungsten to steel, or from steel to tungsten. And here it is the example. Here is the steel matrix, and here is already the some tungsten particles which are made by this additive manufacturing. Density is already quite high, but steel pores and intermetallics, but this is the way to go. So this is how the fusion takes the modern technologies in trying to get the component. Speaking about the component, how can it look like? We don't know, but I think it will be the combination of all of these techniques. For the plasma-facing materials, we can see for the smart systems, for the first wall, the tungsten-fiber-reinforced, tungsten microstructure, tungsten divertor, functionally graded materials just shown now to make robust interfaces, all the joints which are made in several European institutions and in MIFI, which will be protected with tritium barrier to prevent tritium. Here we may have this urethane or tungsten laminate is just shown and feature the corrosion barrier towards the pipe. Most probably this component will be uniting the present concepts. This will end up my lecture, and I hope I was able to show you, to convince you that we will have the extreme conditions in fusion plant, power plant, which will require new advanced materials with unique characteristics. Plasma-facing materials must combine performance, safety, and provide robust interfaces to the structural materials and need to be technologically manufactured. We've seen that the tungsten-fiber-reinforced, tungsten microstructure, tungsten could be used in the divertor, while tungsten alloys are suggested, let's say, for the first wall. Laminates can be used for the heatsink materials, and for safety precautions, permeation barriers can be used during the regular operation, whereas smart alloys can show their features during the accident. And it is, I would say, first I had a feeling that there is all competition, they are fighting with each other. But maybe some of all those concepts will inherit from each other, and many of proposing concepts will likely merge. For instance, now we're discussing the smart fiber reinforced tungsten, using instead of tungsten, smart alloy powder. And of course, we see the boost of the technology, which is coming here. With this, I'm finalizing here. If you want to learn more and you learn to have a glimpse what is the place of these materials, I can advise you to have a look to our new chapter on fusion reactor materials. You can get this access either via Elsevier, or you can send me email, I can send you the copy. This is the part of the huge encyclopedia of nuclear energy, whereas one volume devoted to the nuclear fusion. In total, I think there are 12 volumes. You are very welcome to read all of them. With this, I'd like to thank you all our sponsors, which actually contributed to this efforts. Thank you for your attention, and I'm glad to hear your questions.
Thank you very much for the very informative and entertaining, interesting talk. And now it's time for questions.
Hello, thank you so much for the great talk. I really enjoyed it a lot. I have a question about the materials that make up the smart alloy. What are the conditions or the characteristics that we look for to find the material that would make up the smart alloy? What are we looking for? How to choose the material to create the alloy? And also, is there alloys for graphite? As I know that the tungsten is the material that the divertor is made of, but we also have graphite walls. So is there more alloys for graphite, or is that been tested? And thank you so much.
Thank you. Thank you for a nice question. Indeed, there is a set of the conditions. I simply took this off, let's say from this lecture. Maybe I will make the separate lecture for the smart alloys. There are several boundary conditions for these alloying elements. First, they need to be suppressing the oxidation. And there are very few materials which are good in this. Chromium is one of the examples. Another is that they should not be, for our nuclear fusion, radioactive. So they should not have a radioactivity higher than that of tungsten. Otherwise, we will not gain anything with the radioactive walls. So this will further limit the choice of the elements. They should not create volatile oxides, of course, because otherwise, again, we will not win this game. So it all for fusion. It all for fusion limits the amount of the material choice or element choice for very few, like 5 or 6 elements, which are potentially under the question. So we ended up with yttrium because of the combination of these properties. Interestingly enough, beyond the fusion, we are now thinking about extension of the smart alloy technology for concentrated solar power stations, for instance. Here, other elements which are impossible for fusion, like aluminum, may come into the plane. Aluminum is perfect in suppression of the oxidation. Unfortunately, it's highly radioactive material. It can be really very activated. We cannot use this for fusion. But for the non-fusion environment, we can use this. For carbon, in fusion, it will be very difficult because if we speak about the power station, we will have a lot of neutrons. The carbon is becoming activated and produce carbon-13, but this is half of the problem. But carbon-14 has really long decay time of several thousands of years, and it's highly activated. So it will be difficult to maintain carbon as a fusion material, unfortunately, because it has also a number of advantages. So it does not melt, for the fusion devices. But we might think, let's say, about other non-fusion applications. I know that the tungsten carbide alloys, they are really very nice and very, very ductile. So people wanted to use the even small tiny fraction of carbon even in fusion environment in non-loaded parts. But as a plasma-facing material, this will be difficult.
Hello, Andrey. Thank you very much for your nice and didactic lecture. So this development of advanced materials is very important for the future of fusion as a sustainable energy source. Now, on the way to demo and future fusion devices, testing will have to be done. So you showed already testing PSI2 and Magnum. But how are you planning to test the effect of neutrons in which devices will this be done in the future?
So thank you very much, Guido, and it's very nice to hear you and to see you. In fact, this program is already running. We are not the only one who are doing the smart alloys. Our Spanish colleagues in CEIT and in San Sebastian are doing them using HIP, and they have already exposed these self-passivating materials in the BR2 reactor in Belgium. The results were very interesting. So it's appeared to be that, I mean, ITER continues to surprise us. So, I mean, it really made the annihilation, or let's say the reduced formation of neutron irradiated effects. So it didn't, let's say, it suppressed the grains swelling. So it appeared to be the introduction of these nanoparticles actually makes the material much more robust. And these are the first results, I think, up to the 0.1 dPa dose. We, here in Jülich, together with our colleagues in Japan and in States, supply several smart alloys to be exposed in Oak Ridge. It will be up to, I think, 3 dPa, but this exposure will take something like 3 to 5 hours, so 3 to 5 years. So it is, I think, something like 2026 where we have these results. But right now, the results were surprisingly good. They were reported by Dmitry Terentiev in the last ICFRM.
Thank you.
Okay, Ekaterina, I'm just reading. We have 2 more questions, I think, and 1 remark. Valerian Shaw, I would say you send me please email. I will reply with the chapter. Dita, nice to hear you. You are asking. I was wondering if the smart alloys are also exposed so far in tokamaks or only in linear device like PSI2 and PSI. Yes, they were exposed. They were exposed in ASDEX upgrade. The point here is that if we speak about demo and fusion power plant, which is supposed to be quasi-stationary, linear devices with their long exposures and high fluences, they really make the excellent opportunity for the exposure. Whereas in the current tokamaks, we will be facing of the ramp ups, ramp downs, several other effects. The plasma parameters will not be so stable. So we had this exercise, and you need also to find the zone which is the erosion dominator zone in the tokamak, which is quite difficult, so to say, on the first wall. Unless we go and we actually plan to make the long-term tokamak experiment to see all this zoo of the, let's say, of the materials. But on the relevance right now, the linear devices and on the proximity of attaining the demo near wall conditions, the linear devices at the moment have a lead. That's why we were really very targeting these devices, targeting the high fluxes, targeting the temperature, because look in the current tokamak where we can get 600 degrees C for a year of operation as a wall temperature. So we need actually heat these components. It will be much more complex in comparison to the linear device, which it can be, bless you, can be realized in the relatively simple arrangement. So therefore, yes, we do plan, but our interest is maybe the devices like Wendelstein, which have a long pulse where you can maintain, let's say, the first wall element, and after 1 year or 2 years of operation, get out the smart alloy first wall element to see how it goes. So this is actually our focus right now. Giro asked, what about beryllium? Beryllium is very nice material in comparison, for instance, to carbon, because it has the mild chemistry with deuterium and hydrogen. Unfortunately, it is a rather light element. And if we speak about quasi-continuous power plant operation and these huge fluences which will impinge on the beryllium, it will not hold this. This impact, so it will be sputtered fully, and we can only allow ourselves very thin first wall. Imagine this first wall for demo, it is only 3 millimeters thick, so it is very small crunch, so kind of shield protecting the underlying blanket and structural elements and all infrastructure. Yes, Dita, thanks for answering. Next greetings from Wendelstein team. So we will meet soon, probably.
Thank you very much for additional clarifications. I saw some questions in the chat. If you could share your email for contacts, is that okay?
Yes, it is okay.
I will post it then.
Yes, and Andrey, there are also a bunch of requests for the slides. So maybe if you could share them with us to distribute with some of the people.
I think it is no problem. I think we will discuss technical details with Ekaterina how to do this. I mean, I have no problem. It's a huge presentation of 60 megabytes. Yeah. So it is not that I am simply shooting this email, but yes, sure, we will find a way.
Okay, that's perfect. And in addition, I see one extra question in the chat from Jose Francisco del Valle Mojica, and it's related to the sintering powder process. And his questions are: what are the challenges with regard to tolerances? Can high precision pieces be produced under this method for fusion processes? And are high precision tolerance not a concern at the moment?
Okay, so here the point is the following, that we are dealing with refractories. You know, if we are dealing with refractories, first it is very high melting point, and also it is also heavy powders and quite specific chemistry on all of this. But the melting point is the largest caveat. So you mean to have 3,500 degrees C to melt tungsten, which is not a piece of cake. At the moment, there are pilot studies there, and as you see, the initial element here. So it is, you see, it's quite rough. But if we go, let's say, and which you need anyway to make the machining, you can achieve the tolerances which are the function of this machine. It's not the manufacturing technique. For instance, the Jülich device can achieve the tolerance of now already below 1 micrometer. This is industrial device. So if you see the tolerances within, let's say, for ITER divertor, they are in the range of the millimeters for such elements for entire road, for instance. So the most important here, I think, it is even not the tolerances, but the density. If we can create dense material of this form, we can start machining the surfaces. It will be more difficult for complicated shape, which you cannot after machine. But at the moment, we are not that far away here. The question is here, to try to make the entire element with the pipe or whatsoever by introducing different kind of the powders. This will be really interesting.
Thank you. I guess that perfectly answered. Yeah, I can see in the chat that Jose was satisfied with the answer, so thank you very much.
Yes, sorry.
Please, Vadim, go ahead.
Yeah, thank you. Thank you. First of all, very nice presentation. It was very interesting. I appreciate it. So I have several questions actually. So first one regarding the technique for manufacture of fiber tungsten material, because it wasn't mentioned. It's interesting. What is your assumption about possibilities to cover all vacuum chamber? Because okay, the Q is really high for demo, so the chamber should be also pretty big. So the next question is, oh, you can answer to this, and I will make a question for an answer if you want.
So first starting with first starting with demo stuff. In fact, actually, it is not that big. It is relying on the good isolation, magnetic isolation, and good plasma confinement. If we look to, for instance, those results which I show here, they are all written in this report. And in fact, actually, I think it is not a secret. So this report, I think, is available in the internet. Here, Vadim, you can really see various demo designs. Yeah? And you can see the geometries which are targeted. This is model A, B, C, D. So you see they're different on the gigawatt of fusion power and the blanket design. But the largest is a little bit larger than ITER. So that's why actually I used this ITER-like scaling to investigate the effect of the hydrogen release. The second question on tungsten-fiber-reinforced techniques, there are several techniques. And actually there are still competitive techniques of producing this. And I'm in fact very impressed how these guys actually did these things. So first it is a kind of fast where you simply putting all these fibers in the matrix and sintering. Initially, one needs to deposit this ITER layer as a barrier because it has to have the weak interface between the matrix and the wire in the, for instance, magnetron device. So all these wires first are deposited with ITER, and then it is put into the fast device and sintered as whole. In such a facility, as you might see here. Yeah? So here you can simply add these fibers inside. So these are one of the really most promising technique. Apart from this, there is a chemical vapor deposition, which simply it's emerging in the of this matrix. Basically, they're putting the skeleton of these fibers and having the tungsten hexafluoride gas react with this, so fluor goes out and tungsten remains in this. here they can make really the big samples with quite good density, but the process is rather toxic, as you know, by evacuating the floor. But what they really now doing since last year, I was really entrained by this, they figured out the technique of yarns. So basically this is not the single wire. So they're making like, they're collaborating with Textile Institute. So they're bending 3, 4, 5 wires to one bundle. And instead of the single wires, there are bundles inside the matrix. So therefore the effect of these fibers, so to say, combined fibers, they are virtually unbreakable. So you really need to make a lot of power to break this bundle. You can imagine if you bundle all these fibers. These are now presently produced either with the chemical vapor deposition, but I don't see the crucial problems of making them using fast. What we now are discussing, since both smart materials are going to the industry and available in kilograms, we did make one attempt. It was not successful to make the tungsten smart alloy matrix and tungsten fibers inside. It might work, but it is not good for the oxidation. Since we have now kilograms, we may have a chance of making the fibers out, the smart fibers. And this can be an interesting combined material. Thanks. I hope I answered.
Yeah, thank you. And your assumption for mass production, so in order to cover all this chamber, so what power facility should be, for example, I don't know.
So this one, so you see, these are 3 samples. Yeah? These are three samples, each of which 10 by 10 centimeters. So if we cut this, we will get 4 quadrants, let's say, like for ITER. It is industrial facility. The entire duration with the cooling was, if I remember correctly, 20 minutes with cooling. Full automatic process at the end. So you're basically pouring this dye with the powder, and then you're getting the sample which can be ground. I do not see any obstacles of making, instead of this industrial facility, 10 of them. They will cover square meters in one day, and we have to achieve around 1,000 square meters. A couple of months, I would say. And the materials, the point is also here that this fast technology, it is not very, I would say, it is not very young. So it is something like several dozens of years already, but now it's going really to the industrial scale, and there are more and more on the market. So the price of this device, which has a total power of 150 kilowatt, I think, so it's not the end of the world, so to say, the prices also become tolerable. And in fact, those devices which these samples were sintered are industrial devices already from Dr. Fitch.
Okay, thank you very much. And may I ask another question?
Yes.
Yeah, it's very fast, but just interesting, because regarding multi-layer composite, there is silver used, and if I'm not mistaken, it's irradiated material under neutron flux impact. So, but however, according to safety regulation, which is used, for example, in ITER, yes, materials should be chosen in ALARA principle. So,
yes.
Did you do any analysis how to impact on material radioactive decay, for example?
Yes, I mean, the answer will be, you're absolutely right. The silver is not allowed for the fusion purposes. This was this first try and error method, which our colleagues used to see if this concept works at all, to see if there are no water stones and so on. If you can go here, there is no silver anymore. So this is basically like a layered, functionally graded material. So we can play with the thickness a little bit. We can play with the amount of the layers in order to accommodate different coefficients. But the silver was used only for the first time to see if the technology works, if we can at all make such a laminates. It is, strictly speaking, not fusion relevant.
Thank you very much. It's very interesting. Last question. So yttrium, when you add yttrium to alloys, okay, it may make materials magnetic. Is it alloy magnetic or not? It's a simple question. Thank you.
It will not alloy magnetic because we have 0.6% of yttrium. So this is actually the kick effect here that, I mean, here we can see it's quite a lot, but in total it is 1 atomic percent. So it's really in very tiny amount, located in very precise locations, and doing until now not fully explored by very interesting job in many areas. If we would have another hour of our investigation, I could show you the let's say the protective layer, and this is what we're now investigating with the Oxford colleagues and Warsaw colleagues, how this yttrium at all do this in protective layer, because here you see nanoparticles. In the protective layer, it is pure chromium, which is framed by yttrium. It is really like a holding, like gluing this chromium in between. And this is only something like 5 to 10 nanometers thick. And there is nowhere, anywhere yttrium at all, but it is continuous layer. What it does, what is the function, we don't know. It is terribly stable and it is really very dense.
Thank you very much. Thank you.